Welcome back. Now we are moving on to a new part that is on, it's a bit special. It's not really like a new technology or something. It's just like taking a step back and thinking about performance. When you have to build programs like that manipulate terabytes or petabytes of data, and you want to use Spark, MapReduce, and so on, how do you make it fast? So I'm going to focus on performance, and productivity will come later with JSONing. But before I do that, I have a question for you. Of course. So let me find where it was. It's probably hidden somewhere here. Yes. So you know that when you go to the very small, the world becomes quantized. When you move at very large speeds, some things get distorted. And so I'm basically asking you the same question with large quantity of data. What happens if you have enormous quantities of data? Is it still behaving the same, or do things start to happen in a strange way? So the first possible answer is that the overall execution times of jobs start to be unpredictable, and that leads to massive discrepancies and unpredictability of the results and of the latencies. The second answer is that the execution, on the contrary, becomes much smoother, uniformly distributed across machines, and more predictable thanks to micro-partitioning techniques. And that works because of the central limit theorem. Answer number 3 is that a few nodes are going to keep taking significantly more time than average to complete the execution of their tasks. This is called tail latency. Careful, I'm good at making up stuff. Or nothing, we have designed our beautiful architecture so well that everything scales up and out smoothly. Steady as she goes, Mr. Chekhov for the Star Trek. All right. So did I start it? I don't see any. I didn't. Oh, no, I didn't start it. There you go. What do we have? Yes. Aha, we have not a majority. So the majority in predictability of the results are fine. Correctness, that's totally fine. It's in fact a latency issue. And that I will explain in the coming lectures. So I will explain. But basically, you might have observed, it happens when we do the live MapReduce, that some students take longer to do the mapping. This year, it wasn't really noticeable, but in previous years, there was usually 1 or 2 that took forever, which was great because that's exactly the points that I wanted to make. All right, so this is good. So now I'm going to reload the slides. Okay. So normally it's all good. So now let's get started. Performance at large scale. So we are here. We covered all of this, so storage, encoding, syntax, XML and JSON, CSV, data models, the XML info set, the JSON data model, data frames, validation, JSON schema, JSON, XML schema, and the generic way that the type systems work, processing with MapReduce, with Spark. So we are approaching the end of the semester, all right? We've done some querying with SQL, but only for tables and data frames, and we will continue with JSONic. But now it's a moment to, it's a good moment to take a bit of a break. So what typically happens when you decide to launch a job to a cluster, and here it doesn't matter if it's Spark, if it's MapReduce, it could even be just a local Java program or whatever you want, like any computer program of any complexity. What is for sure is that there is a bottleneck somewhere, always. A bottleneck, so we call it that way because it basically is this visual that you can have in mind, is that some part of the computer, of the resources. Let me reactivate the audio. All right, so something happens. We just suddenly got disconnected from the network, and but it seems that it didn't happen to you, so it's only in the lecture hall. So I just need to load my slides again, and then we'll continue. Okay. Bottlenecks. So some parts of the system are going to not be fully used. And some other parts of the system are completely fully used, and they are the reason why it's slow. Understanding this, so now it's abstract, but I'll explain in more details, is the basics of debugging, but not debugging for correctness, but for performance. You have a computer program, you want to make it faster. The first thing you need to do is find the bottleneck. If you work on something else than the bottleneck, that's totally useless. You have to find the bottleneck and focus your efforts on fixing the bottleneck. You know that thousands of years ago, people could do math and physics and pretty much know everything that was the knowledge at the time. But now, even in computer science, nobody can understand everything. And there are plenty of people in the department that deal with hardware. I don't know the first thing about hardware. I mean, I just know on the abstract perspective that there's some memory, there's some CPU, there's some disk, and there's some network. In fact, that's all I need to know for the purpose of data management. But basically, this is the level of abstraction at which we look at things in performance for big data. We just focus on these 4 abstractions: memory, CPU, disk, network. What I can tell you is that you can take any job going to be too slow for some reason. One of these 4 is going to be the bottleneck. One of these 4. And you have to find out which one of the 4 is the bottleneck. So maybe it's the CPU. How do you notice? Well, for example, you can SSH yourself to the machines and so on and look at the CPU usage, and you see it's all the way to 100%. And if you look at the memory usage, it's used, but not fully. The disk doesn't seem to be full, and also the bandwidth reading from the disk is okay, and the network is basically idle. That's the case where we have a bottleneck with the CPU. The term that we use is CPU bound, right? Your program, the execution of your program is CPU bound. That means that you need to do something about your code, right? It's a compute problem. Or you log onto the machine, you notice, no, it's like 80% CPU, 60% CPU, it's not fully used. The memory is also not fully used. The network is transmitting some data, but it's not at the bandwidth of the network. But you notice that the disk is reading like crazy or writing like crazy. And it's actually reading and writing at the maximum speed that you could possibly read or write from. This is I/O bound, more precisely disk I/O. I/O for input output, right? Input output, we just say I/O. So this is disk bound, or it's memory bound. So you connect to the machine, the CPU is at 60%, the disk is not reading at full speed, the network cables are not overloaded, but your memory is completely full, and it's so full that it's starting to swap and try to do what it can in order to execute your job. This is some of the worst, because that actually almost kills your execution when it starts to touch the memory, right? So, for example, what could happen with MapReduce of Spark is that it starts flushing things, and it doesn't fit in memory anymore. Or it's network I/O bound. It means that neither the CPU is fully used, nor the memory is full, nor the disk is reading or writing at maximum speed, but the data is shuffling like crazy over the network, right? It's clearly a problem with the shuffle and the communication. What I can tell you for sure, well, I will not call it a theorem because it's more a practical thing, is that it's one of the 4. There's no other way. It's one of the four. And there is not 2 bottlenecks. The odds of 2 bottlenecks are very slim. There's always one bottleneck, right? It might be a bottleneck by far or a bottleneck by not so far, but there's always one bottleneck. So your job when you try to make it faster is to just identify the bottleneck, and then you know what to fix. And again, how do you identify it? You really have to log into the machines and look at the CPU, the memory, and so on, and see if that's the problem. There's other tricks, like for example, when you try to execute a query over the data, a complex query, what you want to do is measure the time that it takes you to execute your query on the one hand. And then what you want to measure is another query that only reads the data, maybe writes it back or something, but just that. And then you look at the difference. And if you notice that there is a considerable difference, then it means it's not a disk I/O problem. It's probably a CPU or memory problem. If, however, the speed of your query, the time that it takes for your query is more or less the same that it takes to read it from disk, it means that this is a disk I/O bottleneck. So these are some of the clues that you can get, right? For whom does that make sense? Right. So it's a little bit like Sherlock Holmes, right? You have to do your investigation and find out where that bottleneck is. And that really just requires a bit of thinking and out of the box. Yeah, that's it. There's also profilers, by the way, that can be helpful. Now, I'm going to say something extremely important. It's so important that that might be the lesson number one when you use MapReduce, and this is what many people do not get. The reason number one why you should be using MapReduce or Spark is if your problem is with the disk I/O. This is the main reason why you use MapReduce or Spark. Why? Because once you hit the limits of one disk on your laptop and you're reading it at maximum speed, anything you will do is useless. You can improve your code, you can do whatever you want, it's totally useless, right? So you're stuck with the disk I/O. Then it makes sense to move to the cluster because then you read in parallel. And then the I/O of the disk is going to add, it's additive, right? All the data that you can ingest into the data center. So this is very important because there are people who use Spark or MapReduce when this is not the problem. It's not actually disk bound. I have in mind like meteorology, for example, or climatology, when you try to do CPU intensive work, that shouldn't be with Spark or MapReduce, because when you try to predict the weather, your problem is not reading from disk, right? It's using the CPU to compute the models. So and then it's HPC, right? High performance computing. But you really have to have this in mind. If you're using Spark or MapReduce, but your problem wasn't the disk I/O, then maybe there are other solutions. You can reduce the number of machines probably and save yourself some money in order to improve it. Okay? So I just wanted to make sure that this is really clear. Now, in order to measure stuff, when you do your investigation to find the bottleneck and understand if and how you can actually fix it, you need to think with these things that I told you earlier: latency, throughput, capacity. So these are all the things that you need to have in mind. So the latency when you start receiving, for example, the data. I gave you this whole scale, you remember, all the prefixes. Who knows them by heart now? If you don't, then you should still learn them, but you have to know them by heart. There's two more that I should also add them here. There's also 27 and 30 now. And these are the equivalents on the micro level, right? So milli, micro, nano, pico, femto, atto, zepto, yocto, right? So it's a good idea to know them too, even though zepto, yocto, you will probably not see yet in big data. Femto and atto, you start seeing them. So femto, for example, femto cells, you might have heard, and atto in physics is also the sort of scales that with time we somehow manage to reach. But anyway, for the sake of big data, you at least need to know these four that are relevant to a computer system. Now, I'm going to give you a few orders of magnitudes, but you really should take them as orders of magnitudes because this is really depends on the computer, it evolves over time and so on. But basically, you have to have in mind that if you are looking at the CPU and the registers of the CPU and the assembly code and so on, then you're basically looking at nanoseconds in terms of typical times. As soon as you start going to the cache, you might add a digit or go higher. Then when you go to the memory, it's in dozens or hundreds of nanoseconds. Then when you go to the network, it's microseconds. You see, you're looking at larger scales now. The network is already in meters rather than just inside the CPU. Reading like 1 megabyte from memory, hundreds of microseconds. The disk, so the disk is going to be even slower than that. So when you read from the disk, then now you're in milliseconds, right? If you're interacting with the disk, and then if you think in thousands of kilometers and send data to North America and back, then that's hundreds of milliseconds or hundreds plus milliseconds. By the way, it's not the speed of light. The internet, that's actually, there was a professor who was looking into this at ETH. The internet is slower than the speed of light because it doesn't propagate in straight lines. All right, but you have to keep it in mind, and this is the reason why when you use data centers, you want to try to have the data like in Frankfurt or in Zurich, rather than in the US if you're dealing with it from here. Okay, so these are just the orders of magnitude. I'm not asking you to learn that by heart, but at least if I tell you that you just measured that you shipped something to the US and back in a nanosecond, something's wrong with the laws of physics, right? So you really just should know the orders of magnitudes. Why? Because when you think about the bottlenecks, you can do quick calculations on a napkin, right? You can look at the size of the data, a few divisions, like just primary school math, and you can just quickly estimate some very coarse orders of magnitudes and then compare it with what is actually happening. That is very useful for the bottleneck. Then you have the transmission of the data. Again, these are just a few examples, like the typical speeds of the network. Now we are at gigabits. You heard like die schnellste Schweiz der Welt and that kind of motor, right? So in a data center now we are typically at 10 gigabit, 100 gigabit, and I think even terabit Ethernet is arriving. For HDDs and SDDs, now it's probably even higher than that. But when I measured it at some point, it was like in the hundreds of megabytes per second. With SSDs, you can probably go a bit faster than that now. Reading and writing to a drive, of course, also depends on whether it's sequential or it's all random access, right? So typically, that also plays a role when you read from disk for an HDD above all, because there's a rotating head and so on. For an SDD, it's less of a problem. All right, so just to give you the orders of magnitudes. The disk, it's very useful. That's probably the most useful in the case of MapReduce and Spark, because knowing roughly these speeds, if you have a data set like of 1 gigabyte or 10 gigabytes of data, it's just a simple division to have a very rough estimate of the time it takes to read it all. And that gives you a baseline for the measurement of your query, right? Because if you're already at the baseline, then you know you will not do better than that, except if you parallelize more. Now, there is something that you have to have in mind in terms of the vocabulary, is that latency can be used in different ways. I use latency in the context of the lecture, it's just a matter of definition, as the time it takes to receive the first bit of data, right? It's the waiting time until you start downloading. Some other people use latency for until the end, from when you send your request to receiving the last bit, right? It's just a matter of convention, but you have to have it in mind. But here we'll call it total response time rather than latency, right? So it's the time you wait until the first bit and then the time of the transfer. Okay. Now, when you want to look at your bottleneck, you are interested in the total response time, right? This is what you want to measure, typically when you put the fancy charts in the papers. So now the sort of things that you want to measure, if you finally found the bottleneck and you finally found out how to fix it, and then you go ahead and fix it, then you will want to measure the difference. So you're going to measure the total response time before and the total response time afterwards, right? And then you do a division. It's the old time that it took divided by the new time that it took. For some reason, I wrote latency in here because somehow I had in mind the people that use it. Maybe I should have written total response time instead, right? So I should maybe redo that one. But here I really mean the total response time divided by the total response time. So then here's an example. Imagine that in total, before the improvements, your query took 3 seconds, the total response time from the beginning to the end. And after you have implemented a fix, or done something, it only takes 2 seconds. Then you can estimate a speed up by dividing, and here you would say it's 50%, right? 1.5, so plus 50% in speed up. Okay, for whom does that make sense? Right? You just do the division. All right. Now, if I use that in a special case, I am applying it to a special case, that you have a query that is not optimal, and you try to modify your code by parallelizing. Imagine that 30% of the query is parallelizable, 70% is not. Could be the shuffling, for example, and 30% is the non-shuffling. So imagine that on the part that is parallelizable, you double the number of machines or something, so you manage to be twice as fast for the parallelizable part. Then that's going to be the 30% that gets shortened. So now you see the formula. Before it was 1 as a basis, right, renormalized. Now, after my fix, I have 1 minus P, that's basically the part that was not parallelizable. Now plus P, but P is divided by S, because now I might have increased the speed of execution. So instead of taking 1 minus P plus P, it's 1 minus P plus P over S. That's the part that I parallelize more, right? And so an example of that, if 30% I got a speed up of 2, is 1 divided by 1 minus 0.3. So that's the 70% that are not parallelizable. And then I have the 0.3 that was halved. Now it's 0.15. And I get 1.18. Now you see that it's less impressive, because at first I told you I multiplied by 2, I made it twice as fast on the part that is parallelizable. Sounds very impressive. But now if you look overall, it only improved by 18%. So that's much less than the doubling basically means plus 100%. Right now it's just plus 18%. And the reason is not everything is parallelizable. So when you fix a bottleneck, always remember that if you parallelize, not everything will be affected, just a part of it. So that puts it in relative terms. Okay, who understands that formula? Okay, wonderful. Now there is somebody else. So this is what Mr. Amdahl says, and there is another person, Mr. Gustafson, who says, no, that's the way to compute the speed up. Right? So instead of doing this 1 over 1 minus P plus P over S, it's 1 minus P plus SP. Right? So let's compute it again with this formula instead, what Mr. Gustafson is telling us. That gives us 1 minus 0.3, that's the part that is non-parallelizable, plus 2 times 0.3, because now I doubled that speed here, and now I have plus 30%. Right? So now it's a completely different formula. And they are not saying the same thing. So here I get plus 18%, and here I get plus 30%. So now the question is, who is right? They have 2 formulas, and they give you different results. And in fact, the answer is that in one case, so that's on Amdahl's law, you have one problem. I don't know, a matrix diagonalization or something for a specific matrix. And you found a way to make it faster. Then it's going to take maybe 50 seconds instead of 1 hour or something, right? You just made it faster. If that's the case, then Amdahl's law is the one to use. It means you have a specific problem and you just make that very specific problem faster. You get the answer sooner. Now, Gustafson's law has a different perspective. And in fact, this is something you observe in real life. When you make something faster, people will use it more. And so what happens is that if you manage to improve, let's take, for example, I don't know, just out of nowhere, meteorology. Like you manage to divide by 2 the time that it takes for a simulation for doing the weather. The first thing that meteorologists are going to want to do is just increase the precision to basically compute more in the original amount of time. So now instead of getting an answer in half an hour instead of 1 hour, the same answer, instead of that, they will still take 1 hour like the original time, but they will have something better, more workload, more work. So if you take that perspective instead, that it's the computing power that is the same, you keep using the entire cluster for an hour, but you manage to do more things, then this is the formula to use. Does it make sense? Right? So this is the difference. Do you have one problem that now is faster, or do you manage to do more things with the same resources? So constant problem size on the left, constant computing power on the right. Now, If you want to tune to fix the performance improvements, you already know scaling out works quite well to parallelize, right? Scaling up can also work, in some cases, if you run out of options and the memory is a problem, but you need a bit more, sometimes it's just easier to, especially if you're using Amazon, to just take a bigger machine. But you have to be careful not to abuse that, because you should always try to improve the code first, right? But these are the easy, you just need to press a button, you have more machines, you press a button, you have a bigger machine, right? Last resort. This is really the thing you should do at the end, right? Especially because that costs more money. So if you are a startup and you're getting some money from your investors, you really have to be careful because that's going to consume more money. But what you can do instead is try to improve the code first. And very often in a lot of places, people realize that what they thought was requiring a cluster, in fact, works on your laptop. And that's a considerable difference in terms of resources. So basically, you want to scale up if you have, for example, that basically is based on the bottleneck, right? So you can increase the resource that you're missing. But if you want to avoid, let's say, a scale up in memory, what can you do? Well, you already know one way. You use data frames instead of RDDs. You have valid JSON, use data frames, and then you immediately see that the memory consumption is going to diminish. So this is one way. Another way is projecting away unused fields. Your query doesn't use half of the columns in your data frame. Like you have 10 columns, but you only read 5 of them, then get rid of them. Don't even read them from the disk, right? So you project them. That's what data frames are able to do, right? So get rid of unused fields. That's also applying in object-oriented programming. You have to spot in object-oriented programming those classes that gets instantiated billions of times. For example, in RumbleDB, we have an implementation in Java. So we spend a lot of time scrutinizing the item class. What is the footprint of the class that stores the atomics and the objects and the arrays? Because there's billions of copies of that. So this one we need to spend a lot of time on because every bit that we manage to take away from that class is multiplied by 1 billion in terms of memory consumption. So you can, for example, spend time, and that requires a bit of investigation. But for example, if you want to do maps in Java, then you have several implementations, tree maps, hash map, and so on and so on. So you can try to spend some time and figure out which one uses the least bits, right? And that might depend on your use case too. Then maybe you have redundant things. Redundancy can make things faster, but it takes up memory. So if you remove redundancy, it might be slower, but at least you're reducing the amount of memory that you consume. And then, and here I know that many of you took a software engineering best practice lecture, and here it's usually a big disappointment when you start working in systems, and we have to tell you that. But of course, it's beautiful, right? You do software engineering, it's beautiful. It has a lot of benefits in terms of reusability, modularity, and so on. But the thing is, when you are working with a data center with classes that get replicated billions of times and you care about performance, you do not have this luxury. And then you are going to do things that probably would make some people scream, but you have to try to refrain from using inheritance too much. You have to refrain from using, for example, polymorphism. And then there are things that you will see in some implementations, like in systems codes, like in C++ or in Java. Instead of using polymorphism and derived classes, you're going to see a big switch, right? That makes people scream in object orientation, right? But in systems, this is how you do it, because this is how you make it faster. This is how you reduce the size in the memory and so on. So it requires, of course, a deep understanding of the language that you're looking at. So it's really worth spending time to understand the structure in memory, exactly the bit by bit, what it takes. But again, it's very counterintuitive compared to some of the best practices in software engineering. What about CPU? There's plenty of tricks here. For example, you might have too many method calls, right? So there is this saying that you should have 25 lines per method. In systems, not necessarily. Every method call has a cost because it doesn't always get inlined by the compiler. So you have to make sure that you don't get too deep a stack, right, in execution. So especially if you start having plenty of one-line functions that look beautiful in terms of engineering, but then you have this absolutely enormous call stack that makes it slow in the execution. If you're calling overridden methods, that has a cost, right? Yes?
I think you're not mentioning that very often compilers actually do all of this way better than any programmers.
Yes, absolutely. So that is absolutely a fair thing to say. A lot of compilers are able to optimize, but they are not necessarily able to optimize all the way. So at some point where you even sweeping in the corners to get that last bit of memory or that last microseconds of execution time, then you have to do some things manually, and you cannot fully blindly trust the compiler. But I agree that the compilers get better over time. But you know that the problem of optimizing execution is never solved. You can always doing better and better and better and better. And when you have a specific use case, the compiler is designed in general, right, for a general broad range of use cases. When you want to work on a very specific system that you want to tune to the last bit or to the last microseconds, then it's worth starting to look at these things, right? And there are in some style guides, like for example, at Google, I think their C++ style guide is not, but for example, it's disallowed to use inheritance, like in Java. You can use interfaces, but not inheritance. You cannot use exceptions, for example. You cannot raise exceptions, except if there's really an exception or an error, but you cannot abuse exceptions, right? You have to be careful with class hierarchies. From what I heard, a common thing that happened in the labs at ETH when some of you start writing code in systems is that things are going to be slow. And then we look at the stack, like the hierarchy of classes, and there's 18 levels, right? And so you really have to keep it lean. Like the class hierarchies should really not be too deep. Instance of has a cost. So this is where we do these ugly switches, sometimes just to avoid the instance of. Casting has a cost as well, exceptions and so on. So really, it looks like splitting hairs, but when you come to executing billions of times or trillions of times the same thing, you really try to extract that last bit less in memory or that microsecond or nanosecond of difference. Right? Does it make sense? Right. Of course, that's not universal. What I'm telling you here is for big data and, when you have trillions of times. I'm not saying that software engineering shouldn't be done the way it is. Of course it should, right? There's many applications in which it's very important to have clean object-oriented programming. All I'm saying is that in the specific case of data centers and code, like you're a big tech company with billions of visitors to your website, then this is the sort of things that you need to pay attention to. Right. 2 minutes, maybe I can still say that because I already told you that. How to improve the disk I/O, reading from the disk, use Parquet instead of JSON lines, for example, because Parquet is going to store it as a data frame, column by column, so it's much more compact. You even have the ability to do some additional compression using compression algorithms, the same sort of things that you have in zip. There's all sorts of encodings that compress the data more. And so the less bits you have to read from disk, the more data you can store on a single disk, and the less computers you need in the data center in order to read that data. All right, I'm probably going to stop on that slide. All right, so I'm going to continue tomorrow with this. So hopefully we'll finish that part. Then I'll go into the effects on very large scales. And then probably next week, we'll continue with MongoDB, document stores, and then JSONic. Thank you very much. Have a nice evening, and see you tomorrow at 9.